2020 and the prestigious Prime Minister's Research Fellowship PMRF from the year 2019. His research interests include machine learning, bio-inspired algorithms, and human-computer interactions. Thank you.
Thank you, Rakshitha, and thank you, Jayakrishnan. Now I invite Mr. Kannadasan sir to take over the session.
I hope my screen is visible, sir.
Yes, sir. It's visible now, sir.
Yes. So, well, a very good morning to all. I'd like to thank K. Ramakrishna College of Engineering for giving this opportunity to deliver this lecture for all of you. As they introduced, I'm Kannadasan. I'm doing research in the field of human-computer interaction. So today we'll be looking about brain-computer interface, an introduction. It is an interdisciplinary domain where it not only belongs to computer science department or ECE, nothing like that. So it is an interdisciplinary domain which covers almost more than 4 to 5 domains like ECE, EEE, computer science, instrumentation control. So we'll be having a look at it, what it is exactly. To start with, what are the things we are going to see? BCI, basic idea of what is BCI, BCI system, types of BCI systems, and EEG, especially EEG is a technique which is very useful for brain-computer interface and applications, advantages and disadvantages. And we'll be looking at future developments where you can proceed your research if you are interested in that particular domain. So yeah, to start with, man and the world. Yeah, we are the human beings who have all 5 senses. We can see, we can hear, we can taste, touch, and smell. We interact with these senses to the world. So we do movements, and with these 5 senses we sense from the world and we react to the world. This is how it happens. So, but what if when we have if we have a computer, we have to type something. If we are thinking, we have to type something, or we have to give a voice command or something like that should happen. What if what I think in my brain, my computer can understand what I think inside my brain? So that is the basic idea of brain-computer interface. In between your brain and the computer, we are making a direct interface so that there is no intermediate connection. That is what it is. Actions are the mechanical movements, while thoughts are electrical impulses. Thoughts, whatever we think, will be an electrical impulse which is happening inside our brain, but that we won't see. If we measure that electrical impulses, we'll get to see when we'll be getting some waves, etc. Actions are the mechanical movements. So if I just think that I'll be moving my hand, I'll be lifting my phone. So that action is a mechanical movement, right? That is happening outside. But inside it is happening, the electrical impulse is happening. So these two, we are trying to bridge in between. Thoughts are faster than actions. We think thoughts, so many thoughts will be going inside our brain at the same time. So direct interaction with the world through thoughts would be faster. So what if what I think my computer can understand? So that will be easiest thing, a great thing to do. So that is what is the major motivation behind this brain-computer interface. So to start with brain-computer interface, what is it exactly? As a definition, it's a fast-growing emergent technology in which researchers aim to build a direct channel between the human brain and the computer. So you are a human being who is using the computer, and you have a computer. So I'm trying to bring a direct channel between my brain and the computer rather than me myself sitting and typing and giving commands to the computer. It should be able to understand what I think. So that is the major motivation behind the brain-computer interface. So you can see in this diagram where brain will be generating thoughts, which will be conveyed to the computer through some set of signals, through BCA. So I'll be collecting some signals. My BCE system will process that and say that do this action, and computer will do that action, and we'll recognize that it is doing. So this is how it has happened. If you think some 5 to 10 years ago, we were not having, for example, if you want to search a particular song on YouTube, what you'll be doing? You'll be opening particular YouTube application. You'll be typing and you'll click on search. This is how it goes. Like you will be taking the phone and doing all these stuff. Now think of the current situation. Like you have so many advanced technologies like voice recognition. That is a emerged technology which is going on peak nowadays. Like Alexa, so many voice recognition softwares had come, software robots had come. Now, if you just take your mobile and say, "Hey Google, search this song," or open YouTube and search this song, means it will search the song and give it to you. So that is how the technology is evolving. At first, you have to go to that particular site, you have to type, and you have to search. Nowadays, what's happening? It is now we can just give your comments through voice. Your computer is able to understand that what you're trying to convey. Think 5 to 10 years, forward from now. Like we are in 2022 now, assume we will be in 2032. So how things will happen, might happen is, we'll be thinking a particular song, or we'll hum particular song. Not need to even hum. We'll be thinking some particular tune or some song inside our brain, and your computer will be able to identify. That is what it is, brain computer interface. We were with nothing, and then computer came. With the computer, we were given commands through typing or something. Then now we are into voice recognition technology. We'll be moving towards, much more advanced technology with the help of brain computer interface. So majorly, what are the components of brain computer interface? Means there are first generation of signals from brain. So you'll be thinking, even if you close your eyes or open your eyes, your brain is the only thing which works all the time. Like it will be generating impulses. Even if you sleep, there will be some sort of electrical activity going on inside your brain. You can't stop those. You can't control such things. So that is happening by itself. Human can't control manually those things. So that is the first thing, generation of signal from the brain. Then you pre-process the signal, extract the features from the signal, classification, and then finally what device control. So we can take an example for this for us to easily understand. What example you can take is a wheelchair. Like a person who has lost his leg, who is going to control the wheelchair using his brain signal. So how it can happen is, first I'll ask him to sit and collect the signals, brain signals. I'll ask him to think that he's moving towards right direction. So some set of particular signal will be generated. That signal I'll be storing as that this type. Like I asked him to think towards right direction. This is the signal which got generated. And then now I'll ask him to close his eye and think that he's moving towards left direction. So another set of signals will be generated. And then I'll ask him to close his eyes and think that he's moving forward, stop. So such signals I'll ask him to think, and I'll store such signals. Then, of course, any real-time data will have noise. We have to pre-process the data. So how it can be done is, for example, what kind of noises will come is, your eyes will be blinking all the time, irrespective of whether you are thinking right side or left side or straight. Your eyes will be blinking, and sometimes you have to nod your head. So those things will affect your data. So these kind of noises have to be removed and pre-processed. That is what it is, pre-processing. Next, you'll be extracting set of features based on what you're going to work on, and then classification. Like if finally, okay, I designed a wheelchair and I am thinking something. Now I have to do. Now I have a signal. Like I thought inside my brain that I'm moving towards right. So my BCA system has to classify that I'm moving towards right. That is a classification: left, right, straight. What class it belongs to. Finally, device control. Then the device should move according to what BCA said. My BCA system has said move left, move right. Then the device, the wheelchair should move towards that particular direction. So these are the components, basic components of BCA. First, we'll generate the signal from the brain, we'll store it somewhere, we'll process it, pre-process it, process it, extract the features, and build the model. And finally, we'll apply it on some application. So this is a generic BCA system. Again, a kind of same thing, but where BCA part is relying, that is given in this picture. So signal from the signal acquisition part and till this application interface part is where the BCA belongs to. In that, we do pre-processing, feature extraction, and classification. These things comes under signal processing task. So I guess most of you might be from EC department or CS department or whatsoever it is. Signal processing is one of the research domain, or it is an interesting domain where you can work on a project to increase the signal or the signal. You can reduce the signal to noise ratio, increase the signal quality, and noises you can remove, and you can propose some other techniques for good signal processing. So that is one of the research area. So you'll be taking the signals from the brain, will pre-process, extract the feature detection, then application interface. What is application interface? You will be having some set of application, right? Let it be wheelchair, as we took that example. You have, after you classify it, you have to give that command to that particular wheelchair. Wheelchair should understand that there will be a motor, a mechanical. I mean, a motor will be there that will make it move towards the left or right or whichever direction you want to. So after detecting what direction it is, then you have to make that motor understand what to do. So that is where the application interface part comes. Then based on this depends on which application you are using. There are application like spelling devices, neuroprosthetics. It is nothing but a person who has lost this uh, body object like arm or hand or whatsoever it is, and they'll be fixed some additional devices, and they'll be given signals and to move. We'll see in detail about it. Generally, this is BCA. We have these steps, and that is what is going to happen. We'll see in detail about this in the upcoming slides with examples. So we'll start with first step is signal acquisition, right? Signal extraction or signal acquisition. It means the same. It doesn't matter. So different how to take the signal. Okay, my brain is thinking something. I'm going to get signal from my brain. How to do? What is the process? Different neuroimaging methods are used to derive meaningful interpretation from the. Okay, this line looks big. Don't get bother about it. It is easy. We'll split it and read it. Different neuroimaging methods. What is neuroimaging methods? Neuro means like neurons. We are going to read about neurons. So there are different methods to read about neurons are used to derive meaningful interpretation from the brain signals. There are so many methods available. Through which to interpret the signals, like if I'm thinking this, like if I'm angry, my brain signals will be something. So I should be able to differentiate between when I'm angry, how my signals are, when I'm sad, how my signals are. So I have to interpret all these things. So this is what there are different methods available to interpret my brain signals, which are captured by microelectrodes. So these are different methods available. First is EEG, electroencephalography, that is brain. And it is a technique where you will be collecting the electrical impulses happening inside our brain through some set of electrodes placed in our scalp. This is the first method, the electrocardiography. We have MEG, magnetoencephalography, bold MRI. Most of you might have gone through, or not most of you, at least some of you must have gone through any one of these techniques. Like MRI, at least you must have heard of it using with your friends or family members. MRI scan, you must have heard of it. Like you'll be having a big machine where you'll be made in a bed, and you'll be that inside that magnetic resonance thing, they'll be sending magnetic signals, and then they'll be capturing the brain activity. So that is one method. So these many methods are available. However, EEG is the only method which is cost efficient. If you look at MRI, that device, it will be costing in terms of crores. But yeah, similarly, like other methods also, it will be costing in terms of crores. But when you take EEG is like the cheapest compared to any other method, and it is easy to interpret. You don't need any technician. If you take MRI scan and all, you need to have a technician who is well versed with that MRI scan, MRI device. But with EEG, nothing much is needed. When you just know about what is what, like how to use that device, it is like what to say, normal sensor capturing device. You'll be placing that electrode at a particular position. Once you learn about it, and there are plenty of sources available in the internet to collect how to collect EEG signals and the basics of EEG. So EEG is so popular compared to any other techniques. That is why we will restrict ourselves to the EEG. EEG based BCI systems. So what is EEG? An EEG electroencephalogram is a measure of brain's voltage fluctuations detected from scalp electrodes. So what is scalp? You all know that this is scalp, like the skin which is there in our head. That is where we'll be placing the electrodes. So brain's voltage fluctuation. Inside our brain, we have millions of neurons. As you can see in this figure, we have two neurons in this. And there are axon. Axon is the part which is connecting these two neurons. So how brain will do is, I mean, what brain will do inside is there will be neurons. Neurons will be sending information from one to other by means of sending some electrical impulse, like some sort of electrical impulse will be passed from one neuron to another neuron. So what would happen when the energy is getting passed? Some voltage fluctuations will happen. So that voltage fluctuations will be captured on the scalp. So it is happening deep inside our brain, but we'll try to capture it on our scalp. So that is the thing. And it is an approximation of cumulative electrical activity of neurons. What is it? Cumulative electrical activity. So assume neurons will be of very minute size, 10 power minus 5, 6. So in that size where we can't just take one particular neuron's value by a single electrode. With one single electrode will be of this much small size, and inside this size you will be having hundreds and thousands of neurons. So what it is? So when I am placing one electrode on my scalp, I will be collecting so many number of neurons activity, not only single neurons activity. I'll be having a cumulative electrical activity of many neurons, and I'll approximate it. Approximation means what? I'll be just adding. It will be a summation of all these neurons in that particular place. So that is what it is. It is a cumulative electrical activity of neurons, and we are trying to capture the brain's voltage from the scalp electrodes. So to start with basics of EEG background, it has been found in the year 1875, and they started with the rabbits and monkeys. Through the cerebral hemispheres inside their brain, they kept some electrical electrodes they have kept, and they discovered this electrical property that is some sort of signal is coming out of the brain. Then in 1924, they discovered some alpha waves in humans, and then inverted the term EEG, electroencephalogram, has come at that particular stage. And then in the year 1950, Walter developed EEG topography for mapping electrical activity of the brain. So EEG has been, the term EEG has been termed in the year 1924, and then in the year 1950s, we started to differentiate the topography. Like we'll be seeing about the topography in the upcoming slides, how we split the brain area into different parts. So there are different types of BCI. There are three types. One, first is invasive, second is partially invasive, third is non-invasive. So invasive, what is invasive? We'll be seeing. I'll just give a summary of it, and then we'll be seeing about it in detail in the upcoming slides. Invasive is inside the gray matter of brain will be, that is, we'll open our skull, there will be gray matter above our brain. We'll open that gray matter and we'll place the electrodes inside our brain. So that is what is invasive. So it is invasive because we are opening our scalp, this gray matter, and then we are placing it, right? So that is the problem with it. Partially invasive is inside the skull but outside the gray matter. We'll open up the skull, we'll place the electrode inside the skull but outside the gray matter, not actually inside the brain. The last is non-invasive, that is, we'll be placing outside the skull, that is on the scalp. That is what I was talking about, like scalp EEG, scalp electrodes. You'll be placing it on the scalp, not inside. So non-invasive method is the useful method for many type of research, as you can see in this particular diagram. Like this is how it looks like. If you want to collect so many signals from your brain, so many electrodes from each and every part, if you want to collect so many electrodes, you have to keep all over your brain, like what has been shown in the particular diagram. So we'll see what is invasive, non-invasive, and partially invasive. Invasive BCI is electrodes inserted directly into the gray matter. As I said, you'll be opening up your skull near to the neuron. You'll go very near to the neuron and you'll place your electrode into that. So that is what it is, invasive, and then highest quality of signal can obtain. Of course, when you're going, it is a known property, what I can say. You can take a typical example that your friend is talking sitting near to you. You can hear him very clearly. If he's going some 10 to 15 meters apart, you can hear him, but not very clearly. That is what it is. When the electrode is placed near the source where the signal is getting generated, you will get high quality signal. That is what is happening with invasive. You will be getting the highest quality of signal, but are prone to scar tissues buildup. What will happen is you will be placing an electrode inside the brain, right? Over that electrode, some sort of scar tissue will start to build up over that electrode. So that is the issue, and it will try to close up that. That is what our human body is made, right? Like if we get a cut or something, our body will act and try to fill it, like close that particular scar or something. So that is what is happening. Scar tissue will be building up over the electrodes. This is the issue. So invasive, this is what is invasive. Next, we'll see what is partially invasive. Implanted inside the skull, but rest outside the gray matter of the brain. We'll open up the skull, we'll place it inside the gray matter. Outside the gray matter, but inside the skull. Then we produce better resolution than non-invasive BCAs, where the bone tissue of the cranium deflects and deforms the signal. So, what is the plus point of partially invasive? Is it is better than it is better than non-invasive, but in terms of signal quality, it is better than non-invasive, because non-invasive will be placing outside the skull on the scalp will be placing. That is the thing. But compared to invasive, the signal quality will be lesser only because it is outside the gray matter. When the source is getting apart from the electrode where you are measuring the signal, of course, the signal quality will deflect. It will reduce. So it produces better resolution signals than non-invasive BCAs, where the bone tissue, like you'll be having a skull, right? Because you're placing your electrode outside the brain in non-invasive methods. When you're placing it outside, assume that this is your brain, this is gray matter, and you have your skull over it, and then you have a scalp over it. So whatever data is coming inside this from this brain has to pass through this gray matter, has to pass through this skull, and then scalp, and then it has to come to your electrode. So these many layers it has to pass through. So that is what it's saying. The bone tissue of the cranium deflects and deforms signals. So when you get the signal quality will be less. So that is what it is. Then carry lower risk of forming scar tissue in the brain than fully invasive BCAs. So yes, of course, when you are placing it deep inside, you will have the risk of scar tissue buildup. Here, you don't have that much of it. It has lower risk compared to invasive. Coming to non-invasive, it has low signal quality due to electrodes are not directly interacted with the neurons. As I said earlier, when you have your friend very close, you can hear him him or her very clearly and properly. When he is going apart, of course, the signal quality, whatever he is talking, will be audible. But when he is going some 100 meter beyond, even when he is talking, you will hear that he is talking something, but you won't get the words exactly. So that is what is the issue with non-invasive. The same problem. You're placing the electrode not near the neurons. You are just taking it apart from the neuron, and you're placing it outside the scalp. So signal quality will be lesser for sure, obviously, and it is safest. Compared to other two methods, when we think in terms of safety, this is the recommended method, because you don't need to do any surgery, no medical person is needed, no doctor is needed to open up your brain and place this particular electrode into your brain. So this is the safest method, as no surgery is required. And then EEG is widely used for this particular technique. Non-invasive BCA is what we are interested in. So first we started with BCA, then we saw what are the components of BCA, then BCA types. 3 types were there. Among that, first we saw different types of brain signal extraction techniques, that EECG, ECOG, ME, MRA, etc., etc. Amongst that, we chose EEG because EEG was cheaper and efficient than all other techniques. Amongst EEG, we had 3 types, invasive, non-invasive, and partially invasive. Among these 3, we are selecting non-invasive because it is safest for any research. Like we don't need any other intervention. and so we have low signal quality. It is fine. We'll try to apply our signal processing and machine learning techniques to it, and we'll try to get the thing done. So EEG technique for BCA, electrodes attached on the scalp. You can see in this figure a person who's sitting and watching some stimuli, like he'll be shown some video or he'll be asked to do some activity, something will be happening. A video, a monitor will be placed in front of screen. First step is to attach electrodes will be attached on the scalp, on your scalp. So whatever he's wearing, the blue color thing, a cap will be there. So a cap will be placed on your scalp, or a cap is not necessary. Also, if you are well versed with the brain areas and which area have to plot the sensor, the cap will have the locations where to place your electrode. So you'll be placing the cap first, and then the white thing, white dots, whatever is there, is the spots where you have to place your electrode. The electrode will be of a round, thin, small thing, and you'll be placing it on your that particular spot. Electrical signals of the brain are amplified. So of course the electrical signal we got from brain will be attenuated, and it will be very less in strength. So we have to amplify the signal. That is the second step. Then it is transmitted to the computer. The software converts them into technical control signals. So after transmitting to the computer, we will be doing pre-processing, some sort of processing. Then we will be giving the computer some commands. And then these computer commands controls the devices. So what might we say? Whatever steps you have seen so far, like after signal processing, classification, some application interface will be there. That will give you some set of commands to the device, like move left or move right, etc. So we'll see what physical mechanism is. So yeah, I have said like electrode has been placed, will be placed on your scalp, but where will you place it? You can just randomly put it here, wherever you like. No, there is a standardized, internationally accepted mechanism is there to place the electrode on on a human being's scalp. So EEG is required electrodes to be attached to the scalp with a sticky gel. Of course, your electrode will be of some metal. Of course, it will be a silver or gold coated electrode. That electrode won't just stick into your brain. So you have to apply some sort of gel to make it stick to your scalp. So I'll be placing that gel, and then I'll stick it to your. It is like some normal gel, whatever you have seen. It will be a sticking thing, like glue or something. It will come off once you wash off. So you'll just place it on the scalp and require physical connection to the machine. After doing the connection, you can see a kind of wire, right? A red color wire. It is given some sort of cord. That cord will be connected to an amplifier, and that amplifier will be connected to your system, a particular computer or something. So before going on to what are the places where we'll be keeping electrodes, we'll see how brain is divided, what are the brain areas available, and then based on that we'll decide like which part to keep your electrodes on, etc., etc. So to start with, our brain areas basically divided into 4. That is parietal lobe. Parietal is the back. We'll start with the frontal lobe. Frontal lobe is this area, like the front part of your brain. Then occipital lobe is the back area. This excuse me. Occipital lobe involved with it is the back area. This particular backside of your brain is called occipital lobe. Then temporal lobe is this area near your ears. You have this brain area, right? This is called temporal lobe, and parietal, what it comes is in the middle. The mid area, somewhere this area, mid of your brain is called parietal. So your brain area is divided into 4 parts basically: frontal, backside occipital, sidewise temporal, and mid parietal. So each and every area of brain corresponds to different activity. What is parietal lobe is concerned with is like reception and processing of sensory information from the body. Assume someone is touching or you are feeling something. Sensory information is what you are seeing something, you are smelling something, some sort of sensor related, like eyes, vision related, hearing related, whatever it is, this reception and processing of those signals will be processed in the brain neurons in the parietal lobe, the mid part. Frontal lobe, that is this area where it's decided, is corresponds to decision making, problem solving, and planning. And then comes the occipital lobe that is involved with the vision. That what you're seeing will be processed in this backside area. Then temporal lobe involved with the memory, emotion, and hearing and language. So temporal lobe is this area when you're emotionally doing something, or memory related task, or when you're hearing something, this particular area will be active. So these are the basic four areas. So what sort of signals? 1 minute. I will look at this first, and then we'll go back to EEG waves. Electrode placement. Like now we have divided the brain areas into different parts, like frontal, occipital, parietal, and temporal lobes. As I said, where to place these electrodes in your brain? There is a standardized system, 10-20 system, where the electrodes are placed 10-20 percentage, like in space of 10 to 20%. So first you will measure the space between this mid part of these eyebrows. This is called axon, and this part where you can feel, you can touch and feel. When you just go move your fingers throughout this area, backside of your brain, there will be a sudden dip. That is called inion. Where that is where your brain ends. Your brain ends. So you'll be measuring using a tape from this to this to the backside area, and then you'll be calculating the distance, and you'll split it up into 10% and 20%. For example, in general, it will be around 36 centimeter. It will be 3.5 centimeter and 6 point some centimeter. So this is what 10-20. We'll be measuring the electrodes from here. You'll be placing it 10 centimeter, 10, and then this area will be 20. So accordingly, we'll be splitting it up, and we'll be placing the electrodes. So then what you have to do is we have to letter the regions. First, we the entire brain region we split up into brain different regions. In that we we named it as lobes. Now we are going to name the electrodes, because we can't place electrode everywhere, right? We have to spot some particular area and you have to place the electrode over there. And then so I'm dividing the lobes and naming lobe as frontal, F T C O. Like parietal is called, can be called central lobe. Parietal lobe means this mid area, so I'm just calling it as central. So far, the number of exact position, what I'm going to do is I'm just splitting the brain into two halves. If it is in the left side of my brain, I'll be numbering it as odd. If it is in the right side, I'll be numbering it as even. So if it is in frontal lobe and it is on my right side, so this side I'll be naming it as F8 or F6, something like that. So because it is in the right side of my brain, and it is frontal F. If it is temporal, T or something, T6 or 5. If it is this side, temporal means T, and then if, as it is left side, so T3 or T4. You can see a more detailed view on this. What, as I said, nasal, inion, you'll be measuring 10%, 10%, 20%, 10%, like that. You'll be clearing, and then you'll be calculating this. Starting here, frontal, central, parietal, and then temporal, occipital, voice occipital, and then temporal near the thing. So this is the front view, and you can see the top view, how it looks like. The sharp part, which is the nose. You look from here, this will be your central part somewhere here. So you'll be splitting the brain, and like you'll be measuring. Also, you'll be measuring from here to here. Like there will be a dip here. If you just move your finger towards this area, there will be a dip near your ear. So this position you'll be measuring, and this position you'll be measuring. You'll be calculating the mid of that. That is called a central C. And then from there you'll be calculating C, and then you know this also. You know this, and you know the central part. From where you can start to measure. If you notice this F8, F4, Fz, like there will be arc. It is an arc. It will be like this. It won't be in a straight line. All those electrodes won't be in a straight line. That is why it has been given in like in an arc, because you have arc like this. and backside you have another arc, down arc like this, not in the same direction, because your brain will go and it will be like in this direction. So now we'll go on see about the brain waves. Okay, I've placed the signal sensors on my scalp. So what sort of signals I'll be getting? EEG signal I'll be getting. After getting the EEG signal, I have to make some sense out of it, right? So here comes, there are majorly 5 types of EEG waves. That is delta wave, theta wave, alpha wave, beta, and gamma. Most of you might be knowing about this frequency of the signal. I hope you all know about this. What is the frequency of the signal? How many number of peaks a particular signal is getting in 1 second. That is called the frequency of the signal. So based on that, it is divided into 5 types. So in this, you can see in detail, like it starts with delta. Delta means 0.5 to 4 hertz is called delta. That there will be less than 1 bump, or the maximum there will be 4 high bumps. That is 0.5 to 4 hertz of signal. In that case, that is delta wave. If delta wave is happening in your brain, that corresponds to deep sleep. That you are in a deep sleep. You are not getting any dreams, etc. You're sleeping very nicely. Then comes the theta. Theta wave means that 4 to 8 hertz. You can see in this diagram there is like 4 around 1, 2, 3, 4, around 4 to 5 bumps are there. That is 4 to 8 hertz. That means you are doing some sort of meditation or creativity, like you are thinking something peacefully. So you're trying to create something, creativity you are applying and getting it. When you're meditating also, you'll be getting the theta. Then comes the alpha. Alpha is like relaxed reflection. You'll be relaxed state. You're in a relaxed state, like normal state, like you're doing your regular activities. That 8 to 13 hertz of signal. Then comes beta. Beta is like 13 to 35 hertz, where you'll be thinking something like problem solving when you're mathematical doing something on your real life problem solving, whatsoever it is. When you're thinking, your beta wave will be active, 13 to 35 hertz. Like your EEG signal will be like whatever is shown in this particular figure. Then comes gamma, heightened awareness, that you are thinking very seriously about something, or it's for some meditational courses will get you gamma waves. Like that is how to say, but that they will be saying, right, they will be stimulating your brain, they will do some set of activities. So when you do this, what is it, breathing techniques very fastly or something, your brain will be receiving so much of oxygen, it will be highly active. So that at that time you'll be receiving gamma. That is what heightened, when you are in highest awareness state, your brains will be generating gamma signals. So more detailed thing is given here, where at what particular location it will happen. So what does it mean? So that is what is given in the table. You can see like delta, as I said, it is less than 4 hertz. It can happen everywhere. It will be happening everywhere in your brain, occur during sleep or when a patient is in coma. Yeah, I did not say this. Like first, you will be measuring the EEG signal in terms of microvolts, and then you'll be converting into a frequency domain, and then you'll be calculating. Then theta is 4 to 7 hertz, that will be happening in temporal and parietal electrodes. That happens when you are in correlated with emotional stress, frustration, or disappointment. So these are the research findings, whatever has been reported till now. And then alpha 8 to 12 hertz, when it is happening in occipital and parietal lobe, it means that mental imagery task. What does mental imagery means? Like you will be assuming something. You will be thinking that you will be moving your hand. Sometimes we'll do that, right? Like we'll think that we'll move our hand, move our leg or something, but we won't move. That is what is called mental imagery. You will think that you move your hand, but you won't move. That is called mental imagery. So that is related with occipital. Alpha wave will be generated in occipital and parietal lobe when you are doing mental imagery task. And reduce amplitude with sensory stimulation. As I said, movement, hand movement, or whatsoever it is. Sensory organs when it is happening. That is what it is related with alpha waves. Then beta. Beta can increase the amplitude during intense mental activity. When you're doing something very seriously, then it is called then it is related with beta in the parietal and frontal lobe. And mu, lambda are the some set of signals which are presented in the research papers. But basically, delta, theta, alpha, beta, and gamma are the waves which we will be using in the research. Okay, so I got all these things. I know now I've learned what is EEG, what I'm going to do. So where it is necessary, why should I measure my brain activity? What is the use of it exactly? Means we have medicals. I mean, we have the following applications like medical science. That is first thing is in the medical science that enabling disabled people. Assume someone has lost his vision or hearing. How can you assist them? Look, the entire motivation of our technology is to improve the living standard. So that is why we are studying everything day by day. We are doing some sort of research. Why we are doing this is to improve the life standards. At first, we were not having so much technology. People were dying due to diseases. Now they got so many techniques and technologies, some medicines and scanning methodologies. Everything is coming together, and we are trying to improve the human standards. So for that, we were trying to enable the disabled people by terms of giving this vision and hearing. If they can't see or hear, we'll try to place them. Of course, their brain will be working properly. So we'll try to capture the signal from their brain and assist them with some set of BCI devices. Then paralysis treatment, prosthetic devices. Prosthetic devices, as you can see, like if they have lost their leg or hand, we'll be fixing a device, we'll capture, of course, assume the brain will be generating signal to move your hand, but this part is cut. You don't have this part. So what to do is, like, the brain signal I'll capture and I'll give the signal here to move that robotic arm. That is what is prosthetic devices provide by means of communication to completely paralyzed patients. Assume there is a paralysis treatment in paralyzed patient means a person who can't interact with the outside world. So that is the issue. So what we'll be doing for that is, well, of course, they cannot talk it out. They can't say that I'm suffering from this and that. We can capture their brain signals and try to get some sort of meaning out of it. So that can be done. That is where the BCA comes in the picture. Surgically implanted devices used as replacement for paralyzed. Of course, these are the different applications for paralyzed patients, and prosthetic devices are other one, and vision and hearing. Apart from medical sciences, what else I have is general applications. You can see is controlling a robot. Nowadays, robots are evolving. We have so many robots. At first, robots just did our actions. I mean, commands, whatever we have programmed for. And then there comes the voice recognized robots that will understand what we are trying to convey, and it will do the actions. Nowadays, I mean, in the upcoming technologies, we can think of robot like we'll be thinking something in our brain, and robot will act accordingly. So it is a person, a replica of you, and it will be doing whatever action you are thinking inside your brain. This where this can be used exactly is in the military applications. Assume you don't want to lose our lives, right? Of course, human life is very important. So you'll be creating a robot and sending it to the field for fight, and it can go. I mean, it can go, and you'll be controlling it from here. Like a robot can have eyes, so whatever it is seeing, you can see it in the video, and then you can think in your brain that go left, go right, hide here, attack him, etc. So this is a typical example for it. Then comes playing games. Playing games is another like nowadays, like a person who played the games might be knowing about it. Like we'll be giving commands. You can take the Super Mario. Apart from everyone must be knowing about Super Mario game, like jumping, going, this attacking person. That I have to give keyboard commands, right? Now, what if I just close my, when I just say, think in my inside my brain that jump. So when I say jump, that Mario will jump and cross that hurdle. So that is how it can be used in BC when playing games. Then comes emotion recognition. This is very interesting application where what if your brain, your computer understands your emotions? It will be a great thing, right? like when you're so tensed or something, you'll be clicking and it won't load. I think your computer already have emotion recognition system. It's a sarcastic comment. It doesn't have. Your computer is just a dumb machine which can't understand anything. Whatever comments you are giving, it will just do that particular command and finish those jobs. But we need some set of emotion recognition systems. Um, it should uh, it should be able to understand how the user is feeling. If he is in a depressed state, it can suggest, it can understand, the computer can understand and reply back accordingly. So that is one set of application for emotion recognition. Coming to this other thing for physically weak persons to handle the computer, for example, if someone is having some sort of um, issues with moving their hand, like they can do, but it will be very slow because of some medical issues. So what can be done is cursor, for example, this is one typical example, like cursor control. Oh, they'll be having the poor muscle control they'll be having. So for communication, it will be very tough for them. Whatever signals it's getting generated inside the brain can be given to the device directly, and then it will be moved and or else like there can be an additional robotic arm or something which can help them in that application. So everybody must have known about this great person Stephen Hawking. Um, so this he had used a chair which can do so many things. So he can't talk, can say stuff. I mean, what all he can do is he can think, and from that brain they have collected the signal. They try to decode it. So that is very easiest example which we all know in terms of BCA. A physically handicapped man operates a BCA wheelchair. So what it is having is, first we can start with this user. User will be electrodes and signal will be generated. It will be going into the amplifier. From amplifier, a BCA control will be there. So in that, what I'm doing is I'll extract the feature. I'll do some set of so once features are extracted, I'll be giving it to a control interface. What set of feature I'm extracting means, like some mean value. For easy understanding, you can take mean value, variance of that particular signal, etc., etc. So I'll be translating that. Translating means what? Like classification, what he is thinking. So I'm trying to classify what he is thinking. Then I'll be giving it to the control interface. Control interface is the one which will uh, display, like the person can see, interact with that control interface, through which, and then the control will be given directly to the device controller, and the device will move left or right, or whatever he is thinking accordingly. So this is a very easy example of BCI. Apart from this, we have this is another example where a single-handed man interfaced with interfaced with BCA. There are two cases in this particular example. First case is a person who has lost his control in this part. You can see in that the signals are coming, the red color dotted lines. Signals will be coming from here, but the muscle which is here in this area is lost. It is damaged, and so whatever signal is being generated won't be getting passed through this area. So what will happen? This after this, of course, if the signal is getting blocked here, you can't control this arm and sorry, you can't control your fingers, etc. So for that, what I'm doing is I'm going to collect the signals from here. I'm going to place some set of electrodes after this part where it is active. Only this part is not working. Some set of some muscles are damaged. So if I place some set of electrodes in this part after the damaging part, I'll give the signals. I'll pick up the signals here. I'll give the signals commands here to move my um, fingers. So that is what it is given. The implanted electrode in this arm allows healthy muscles to receive signals from the brain to close the hand. Hands closed. Okay, this is one example. Another example is, like, assume that the person has lost his one hand. So there is no hand after this. I am fixing a robotic hand for him. I'll be getting signals from my brain for closing my closing my fingers, hands. So the signals will be coming here, and that particular signal will be converted for the robotic understandable language. The robot then the robotic arm will close. So for that, what I need to do is I have to collect signals, make the person sit, close his eyes, place the electrodes on his scalp, and make him think that he's closing his eyes, opening. So closing his arm and opening his arm. While closing the arm, your brain signal will be different. When you're opening the arm, when you're closing the fingers, hand, it will be different. When you're opening it, it will be different. So this is one example. Another example you can take is Japanese student, as you can see that student is just thinking and visualizing that he is walking inside that virtual environment, virtual world. So, Japanese student walking in the virtual world with the character controlled by his brain waves. So he just assuming that he's walking. The brain waves are getting generated, and he is walking through that particular virtual environment. So these are the different applications of VCA. So, of course, there will be advantages and disadvantages for every technology. We have to check which is higher. If advantages are more, we'll just go with it, right? So, advantages in terms like VCA helps in creating a direct communication between human or animal brain and computers. Our ultimate motto is to connect the computer directly with our brain without any intermediate step. That is what is the major advantage. Also, it provides a better living, more features, more advancement in technologies, as whatever we have seen so far. That is the thing. It is improving our better lifestyle. It is giving more features to us and advancement in technologies. Coming to the disadvantages part, what are the disadvantages? It is risky because it operates with brain. It is given as whatever is given is a general difficulty. I won't say it is a disadvantage. It is a difficulty rather. Why it is so is because when you are working with invasive BCAs, you're opening up your skull and working. So it will be risky. Of course, you're opening your skull and placing a sensor inside. It is a risky method. Effective BCA techniques are as invasive method. When you want it to be working 100% right, then you have to go for invasive. That you have to open up your skull and brain and place electrode. And requires magnetically shielded room and special kind of helmet for medical applications. Oh, these are the disadvantages. But what is the plus thing in this is all these things are for medical related application. So assume you are working something like a wheelchair control or something like engineering application or general application. You don't need these kind of thing. I mean, like you don't need invasive BCA. That is what I'm trying to convey. You just need an non-invasive BCA. So with non-invasive BCA, there is no such disadvantage. You can just proceed. Whatever is being listed here is a general. So including invasive BCA, these are the disadvantages, difficulties. For non-invasive, there is nothing. You can just easily fix the electrode on your scalp and proceed with whatever application you are trying to work with. So possible areas of research in this particular VCA systems are like elderly care and home monitoring. Assume there is some autism child or else some elderly person who is there at home who is having difficulty in talking, or we can just place a sensor with them, and whenever the sensor is going high, you can just you can get a notification in your mobile that they are not well, so that you can call 108 or emergency number and ask them to go to that particular area to take care, or you can go directly. So this is one research area. These all are open areas. Like you can collect the signal and you can design your experiment and work accordingly. Wearable technologies. Now this came before some years. Like this is recent only, like 4 to 5 years it has evolved in this digital watch, digital smartwatch to say. These things were not there before, right? This has sensor, this has temperature sensor, this has heartbeat sensor. So all these things this sensor can do. So similarly, why can't we do something with brain computer interface, like some sort of cap which you can wear it all the time, which will create, I mean, collect the signals and which can do some set of functionalities. When you are having stress, you can see, rather than collect, I mean, getting a stress value from this watch, if you are getting it from here, the source of stress, it will be easy for you to understand. Then emotion detection and classification. This is another domain where whether to say whether a person is happy or sad. Before we used to do like we'll be taking a facial video of a person, facial picture of a person, and say whether he's happy or sad. And then what else you can do is voice recording. Through voice, you can say how a person is feeling, happy, sad, etc. Now, emotion are generated from your brain. Instead of just going to your facial expression or voice recording, all those things you can control. But brain, you cannot have any internal control, right? You can just directly go with BC based emotion detection and classification method. Epilepsy detection and prediction. Epilepsy is typically fits. Brain goes abnormal. Sometimes, I mean, they'll be getting fits when your brain goes abnormal into the abnormal stage. So for this, there is no found treatment till now. They are trying to do. So what you can do is when you are trying able to predict epilepsy or beforehand, it will be easy for you. I mean, it will be a great thing to do in the field of medical research. And then apart from that, robotics in healthcare, like lost robotic arm or hand or leg or whatsoever it is. Robotics in healthcare in another research area where it can be picked up and worked on. So to conclude with, BC is a highly promising research area. It is just evolving, like any other before we had natural language processing domain, signal processing domain. Now we have this brain-computer interface. It's just blooming. I'm sure that in another 5 to 10 years, it will be at peak, like how machine learning and deep learning are ruling the world right now. BCA will be ruling the world in another 10 years, for sure. So, as it is improving the standard of living, it provides high standard of living, it extends our limits. Whatever we think, it is just extending, right? Before that, we were thinking we can, when the person's hand is lost, we can't do anything. Now we have robotic arm. Now we can control it with your brain signals. Like before, you had not like normal hand, the robotic arm will work. So we are extending our limit. There is no. That is what is happening nowadays. So finally, we are into to this quote. I want to quote this. I impart a new level to the popular quote that I think, therefore I am. So what I'm thinking is what I'm becoming. So that with the help of BCA, I'm my brain signals will be I'll be taking that. I'll process that. Whatever I want to do, I'm able to do. I can do. So that is what I would like to conclude with. So thank you for your patience listening. Here I've given my mail ID and WhatsApp number. If anybody is interested to proceed in this research area or domain, you can contact. If you have any doubts, you can mail me or contact me anytime. I'll be happy to help. If you have any doubts, please ask.
Good afternoon, sir.
Yeah, good afternoon.
With respect to BC processing, is there any frequency limit for analyzing that?
Sorry.
You are analyzing with the brain signals, all the things now, sir.
Yes.
With respect to that, is there any frequency limit or something? Any mathematical modeling is there?
Frequency limit as in generally it makes sense till 50 hertz, around 50 hertz, sir. 0 to 50 hertz, like that is what till gamma waves we can think of it. After gamma, the signal will be highly noisy because it will be due to noise and high frequency. We can't differentiate what is noise and what is high frequency signal. So we'll limit ourselves till this 50 hertz, and I think that answered your question, sir. Is that your question or?
Yeah.
Yes.
whether you are using a MATLAB programming or any other
Yes, sir.
language.
MATLAB has all the tools which is needed for this EEG. There is a toolbox named the EEG Lab, which helps to just load the data and plot the graphs, whatever you want to. Even pre-processing, all the things are available with MATLAB and EEG Lab toolbox.
Okay, sir. Thank you. Participants, do you have any queries? Participants? Okay, sir. I will share your WhatsApp number to all the participants.
Sure.
Okay, sir. Now I invite Monica Flo to give a vote of thanks. Monica?
Yeah, sir.
Yeah.
A very good afternoon to one and all gathered here. Feeling gratitude and not expressing it is like wrapping a present and not giving it. It's time to express our gratitude. First of all, I would like to thank Mr. K. Kannadasan, research scholar, for accepting our invitation to give valuable, informative, and expounding talk on brain-computer interface. Thanks a bunch, sir. Special thanks to Mr.S.Prasad Jones Christydass, SEMCE coordinator, for identifying such an amazing resource person for us. Thank you, sir. I also thank our principal, Dr. N. Vasudevan, sir, our head of the department, Dr. A. Kavita ma'am, and Dr. S. Saravanan, sir, HOD Center for Student Affairs, for giving permission to organize this event. Also, I would like to thank Mr.S.Syedakbar, sir, staff coordinator of this event, and the student coordinators Jayakrishnan and Rakshitha. Without participants, events can't be successful. So, I thank all the participants for your active participation and cooperation. Thank you all. Let's aim high, achieve high. Once again, thank you all. Kindly fill the feedback form posted in the chat box.
Thank you. Thank you, sir, for giving this opportunity to share my knowledge. Special thanks to Prasad, sir, for arranging this talk.
Thank you, sir. Thanks a lot.
Thank you, sir.
Thank you, sir. Thank you all. Thank you, participants.
Thank you, sir.